Hi, my name's Steve Wigmark. I teach physics at Mountain View High School in Mountain View, California. And this video and the worksheet that goes with it are meant to be sort of an introduction to radio astronomy that you might find useful before you conduct an observation session using the big Gabbert radio telescope down in Southern California. The first little exercise we're going to be doing here in this video is to measure the wattage of the sun, the total power produced by the sun using some very simple apparatus. So let's get started. To measure the power of the sun, we're going to use a device called a radiometer. And the heart of the radiometer is this block here, which consists of two slabs of wax, and sandwiched between them is a reflective surface of mylar that acts as a mirror. So light entering one surface of the radiometer is reflected back outward, and light entering the other side of the radiometer is also reflected back outward. And we're going to place this radiometer into a frame, and we're going to point it at the sun. And the idea here is we want to sort of balance the light levels on either side of the radiometer, with the sun being on one side of the radiometer and a 300-watt light bulb being on the other side of the radiometer. And when these two light levels sort of balance, then we'll know that the amount of illumination on one side of the block is equal to the amount of the illumination on the other side of the block. And using that data, we can figure out what the wattage of the sun is. So here's the radiometer mounted in its frame. I want you to notice the two halves of the wax block. The left-hand side of the wax block is rather bright. That's because it's pointed at the sun. The right-hand side of the block is dark. That's because it's in shadow. Now what I'm going to do is I'm going to bring this 300-watt light bulb sort of close to the wax block, and I want to see if I can get the two halves to sort of match up in brightness. It's probably a little harder to see on camera than it is to see live, so you may have to trust me on this. But I'm positioning the center of the 300-watt light bulb to sort of balance the brightness. And it looks to me that when the center of the light bulb is at about, right about there, maybe at about the 10 centimeter point, the brightness is balanced. So we're going to use that data of 10 centimeters and the fact that I'm using a 300-watt light bulb to calculate the wattage of the sun. So the way we're going to use this data in order to figure out the power of the sun is to realize that the intensity of light varies as 1 over r squared, much like electric fields or gravitational fields also vary as 1 over r squared, a sort of inverse squared law. So suppose I put my finger at a certain distance away from the center of the light bulb. There's going to be a certain amount of light intensity at that point. If I were to double the distance from the center of the light bulb, then the intensity of light at that point would reduce by a factor of 1 over 4. That is because I've doubled the distance, so I square that and I make 4, and then I take the reciprocal of that and I get 1 over 4. So my finger out here is experiencing 1/4 the intensity that my finger would have if I put it right here. So we can use that to actually calculate what the power of the sun is by setting up a ratio of power to distance squared. So if you take the power of this light bulb, which is 300 watts, and you divide that by the distance squared that the light bulb was from the radiometer, so that would be 0.1 meters squared, that ratio should be the same as the ratio of the power of the entire sun divided by the distance from the Earth to the sun squared, provided that the two halves of the radiometer were in balance. That is to say, they both sides looked equally bright. So that's what I want you to do as a calculation on the worksheet that's associated with this activity.